You're now unmute.
Now I don't have to remember. Toronto. Sir?
Yes, the other side is ready as well.
Oh, okay. Great. So, yes, welcome to the afternoon session and greetings to Toronto. We're going to see video link in a little bit in a minute. So the first speaker of the afternoon is Nathalie Wahl from the University of Copenhagen. Talk to us about Yang Baxter elements and the new proof of homological stability for the mapping class group of surfaces.
Thanks for the introduction. Hello, Toronto. Sorry, no, I feel, I know I'm talking to you guys too. I don't know who you are, but I can sort of try to guess from the few voices we have heard so far. Okay, so I have this very long title that Ian already told us. My goal for today is actually very similar to the one of Yen this morning, is to learn something about the homology of the mapping class group of surfaces, or BDIF, or the moduli space of Riemann surfaces using some structure, right? And more precisely, my goal for today is going to be to give you to sketch a proof of the following statement, which says the ice homology of the mapping class group of a surface, let's say just genus 1 for simplicity, genus 1, one boundary component, sorry, some genus, one boundary components. I'm looking at diffeomorphisms fixing the boundary, and then I take pi 0, so that's the mapping class group, and then I can increase, so I'm already saying it's an isomorphism, pi 0 diff. I can increase the genus by gluing a little torus. So I go from a surface of a certain genus, and I have diffeomorphisms fixing the boundary components, and I can increase by adding a little genus piece. And this is an isomorphism for I smaller or equal to 2g minus 2 over 3. Okay. Okay, so this is a statement, so this is called homological stability when you have such isomorphisms that are given in in a range that increases with some rank, the genus in our case. It was originally proved by Harr with a slope 1/3, where the slope is, I mean, the slope here in the statement would be the coefficient of the genus. So Harr was originally in the 80s proved this with slope 1/3. Ivanov improved it to a slope 1/2, and then Thornton, and roughly at the same time, Randall-Williams with different proofs, and then more recently, Galetius, Coopers, Randall-Williams, and then I'm going to add one more proof to this. So Harr, Vistrup, and myself prove this exactly this same bound here. So 2g minus 2 over 3 for the isomorphism with rather different proofs. So and also I should say there's an older result of Morita that tells you that this is essentially best possible. Now, if we have 4 different proofs that give exactly the same range, it's probably best possible. But there is, there is a discrepancy between these two results, which is maybe once every 3rd genus, it could be potentially one better than what we can prove. But I stopped believing that this is possible because Okay. Anyway, why do so many people care about this particular fact? Well, again, I mean, we saw this morning, the homology of I0 diff, the mapping class group of a surface. So this is the group homology. You could this is the same. It's isomorphic to the homology of B diff. The classifying space of the diffeomorphism group of surfaces. This is the thing that classifies surface bundles. So this is something a number of people like. And it's also isomorphic to the homology of the moduli space of Riemann surfaces. This is also the moduli space of hyperbolic surfaces and all sorts of things. It also shows up a whole lot of places. So a lot of people like these spaces. And on the other hand, so the homology is invariance of this, and the homology is badly hard to compute. Okay, so it's not easy to get at. What do we know? We know some low genus cases. So Fred Cohen long ago computed the genus 0 in genus 1, 2, maybe a little bit 3, not too many boundary components. Bodygeimer and a lot of collaborators over many years made a lot of progress, but it stays very, very low genus. And then we know all the stable homology. On the other hand, this is Metz and Weiss. That means that whenever you are in this stable range, we know the answer. I mean, it tends to some particular homology groups, and we know what it tends to quite concretely, totally concretely, rationally, but also over every prime, you can sort of write down the answer. So this is something. So it's nice to know when you reach the stable range. And except for that, well, Galetius, Coopers, Randall-Williams, they also use their work to compute some of the things that are close to the stable range. So we know also a little bit there, and then there are a few other things, but it is really not much more than that. Okay, so that was for the where are we in the world, and I said I would talk about Yang Baxter elements. So let's go into that. And we'll at some point go back to the mapping class group. Okay, so I start with a monoidal category. I mean, in this audience, I feel like I have to say what I mean. I'm really thinking in sets, right? A good old monoidal category, nothing particular about it, like just plain good old days, right? And maybe it's probably good to have in mind or a linear category, because I guess there are many more interesting examples there, and a lot of this can be done in that setting. But feel free to fill in whatever you like here, and I'm sure a lot of things go through. I don't know what I mean. But this is good old category is good enough for us today, or for me. Okay, what's a Yang Baxter element? This is a not necessary shadow. Go away. Okay. So a Yang Baxter element for an object X in M is an element in the automorphism group of X plus X. Yeah, I can take my object, sum it with itself, and ask for some element, but it should satisfy the so-called Yang Baxter equation. The Yang Baxter equation says B plus 1, 1 plus B, B plus 1. So if I compose the morphisms, I add the identity on X. This is equal to 1 plus B, B plus 1, 1 plus B. This is an equation that is happening in aught. So I'm in M, right? Of X, three copies. So I have an automorphism of 2 copies of X, and I add the identity either on the left or on the right. Right. So this is called the Yang Baxter equation, or the braid equation or relation. And why is it also called the braid relation? But because this is something satisfied by the braid groups. If B was a generator of the braid group, it would look like a cross, something like this. And then when I do B plus 1, I put a little identity on the side. And when I do this, then I would say identity, little cross. And then I go again, cross, identity. Then this should be equal to, I do identity and cross. It should do the same, otherwise it's not going to be true. Like this, and then this, and like this. So this is a well-known, I mean, these two braids as braids are the same. Okay. So that's a definition. What are examples? Well, if M is what is called braided or symmetric monoidal, then you can always take B to be the symmetry for the object X and itself. A braided monoidal category has exactly one of these, and it's a condition that it satisfies this relation. So that's a standard example. The other standard example is you can always take B is the identity on express X. The identity definitely satisfies this relation. So what's the sort of the what is the thing you should keep in mind? The difference if you use two braided or symmetric monoidal structures The main difference is I dropped the naturality condition. I'm not asking this element to be natural. If I take the identity, it's definitely not, does not satisfy the naturality condition of a braid. Okay. What I want to note now is if you have such a Yang Baxter element, B, and then you use the fact that we have this monoidal structure, it exactly tells you that you get an induced map from the braid group on n elements to the automorphism group of A plus X plus N, where A is any other object. So you could shift everything by some object if you like. And what is this map? It's taking the standard generator, the thing that crosses the I and I plus, I know this is microscopic, but you know what I'm writing, I and I plus first, which is the I and I plus first element, the standard generator sigma I goes to, when I do the identity on A plus X plus I minus 1, I guess, and then I do B, and then I do the identity on the rest, X plus N minus I minus 1 probably, something like this. Okay, and this is a morphism from the braid groups, because the braid group Bn is exactly generated by these elements together with the relations that are these braid relations, sigma I plus 1 sigma I is equal to sigma I plus 1 sigma I plus 1, together with the relation that sigma j is equal to sigma j sigma I if they are far enough apart. Is at least 2, I guess, something like this. If you do braids crosses sufficiently far apart, then they commute, and this will be it's implied by the fact that it's a monoidal category. Okay, so we are ready to decide if we use one more board. I do. So I'm going to be very sort of nice to you guys here, and maybe only half nice. So anyway, Toronto, there is no third board, and for Bonn, there is only half a third board. So do with that. Okay, so we have our, I wanted to talk about mapping class groups. I told you about Yang Baxter elements. We should look for Yang Baxter elements related to mapping class group. And I just told you, well, it has something to do with the morphisms from the braid groups. Okay, so we go back to our mapping class groups. And well, there are two well-known embeddings of the n in these mapping class groups. It's the first one. So the first one has to do with the configuration space of surfaces. So to be completely precise, the braid group embeds into the ribbon braid group, which is isomorphic to the mapping class group of a surface like this, a punctured disk, or a disk with, I mean, you can think of it as a multi-leg pair of pants, or what. Anyway, a disk minus a bunch of disks. I want to think of it as a surface with boundary. My boundary is fixed. And and I have n of these, 1 or 2, I have n holes. The braids, these generators we have been talking about, they switch these disks. You take the one, you make them pass across one another. The fact that it is the ribbon braid group rather than the braid group is just the fact that you can take a single disk and rotate it around itself, and that gives you a little more. But there's a subgroup which is the braid group. Okay, so if I look at this, so this is already a mapping class group. If I'm interested in mapping class groups of surfaces of higher genus, then I can just go further in a very, very small arrow. I know diff. And now I'm going to draw the same surface. In my boundary here, I have these little holes. But then in each one of these holes, I'm going to glue a little genus 1 surface with one boundary. Okay, so now I have, so this is pi naught diff of S, well, right, okay, n, 1 genus n, and 1 boundary component. Okay, I can get a genus, and my braid is still there, right? I can still exchange little elements like this. That's the morphism from the braid group. Okay, so I want to relate this to what I was talking about here. I was talking about a monoidal category in which I was picking some element X and some little element B. This just a second. Okay, so what is M? M is the category of it's called the marked surfaces. So these are surfaces S I, where I is an interval included in the boundary. It's a marked interval in the boundary of S. Okay, so that's my category. So the sum is going to glue, we're going to glue surfaces, glue along intervals. Okay, so if I have you see, I'm in trouble now. Did I? I get it. I'll be fine. I'll be fine. I have a plan. So, okay, everybody happy? So, okay, so we have our category. The surfaces have a marked interval in their boundary, so that allows me to define a gluing by saying I just identify these intervals. So to be precise, I'll take half the interval of the one surface and half the one of the other, glue those, and then I'm left with 2 half intervals, or also known as 1 interval. Okay, so that's a monoidal structure, and I can define this in a way that it is really associative, etc. Okay, we have a monoidal structure. What's my X? Well, X is going to be I'm going to take a surface of genus 1 with 1 boundary component and this little interval, right? I in its boundary. And so when I do X plus X, it's going to look like, I mean, I can redraw, I'm going to redraw the picture like this, and you will hopefully agree that this is the same surface, at least. If I glue, is my interval I glued along. Okay, I glue 2 surfaces like this along an interval, I get the genus 2 surface that looks like this. And now I can play the same game as I did before. So you can think of these as little circles, and my element B in the mapping class group of this surface is exactly the thing that switches the two guys, right? So I get, this is B in oat. I didn't say what the morphisms were, right? Oat X plus X, my morphisms are the mapping class group, so by 0 diff. X plus X, and fixing, you could fix the whole boundary or just the intervals. So, I mean, there are a bunch of variants of the definition here. Okay, so that's one example. That was one well-known map from the braid group to the mapping class group of surfaces. There is another one. And it looks like this. So I need to, I'll draw two surfaces. This is at the back, like this, and I'm going to draw another one like this. Okay, and in these surfaces, I have certain embedded circles. I can take a circle here, and then here, and then there, here. So it's a chain of circles that intersect, have intersection number 1. Yes. And so this is here's a fact, is that you can map B2G to this mapping class group pi naught diff of SG1, the boundary, if you want, and B2G plus 1 into pi naught diff of SG1, SG2, but boundary. So this is a surface of, so G is equal to 3 in the picture. If you count, there are 6 circles. So there's 2, this is one of these. This is G is equal to 3 for this one. This is G is equal to 3 for that one. Because I closed it off here, I have one more circle. Okay. So, and these morphisms, they are defined by taking the ith generator of the braid group. You go to the Dane twist along the ith circle in the chain. Okay, so if the circles are far apart, they don't intersect, and the Dane twist commute. That's one of the relations of the braid group. And then the other one says, well, if 2 circles have intersection number 1, then they satisfy this braid or Yang Baxter equation. Okay,
is there a conceptual explanation for why you satisfy that particular relation?
So the question was, is there a conceptual relation why this relation is satisfied? And I don't know such conceptual relation. I mean, you can sort of sit down and draw braids. And, believe me, I have sat down a lot with these surfaces for a long time before I understood what the hell was going on here. And I do not have a conceptual explanation. But maybe if you ask licorice, is your life? Probably not. Okay, anyway. Yes, yes, he is. You could go and ask licorice. Oh, okay. So Oscar is suggesting a nice conceptual explanation, which is by looking at, by taking, considering the surface as a branch cover of, and this is actually also a little bit underlying in what I'll talk about, but yeah, I mean, surfaces can be seen as branch covers over the disk, a punctured disk. And then these, it's possible to see these twists as coming from the same type of picture as the previous one, which is above and behind. Yes, okay. Right, so if I want to make this be in the same in this framework I'm talking about, then I would want a category M again, a monoidal category, and an object X, and then this Yang Baxter element B. Looking that does this. So I drew the surfaces in a way that is meant to be suggestive for these things, but maybe it's not so immediately clear. So M, what is M? Well, it's going to be a category of marked surfaces. So same as before, but I'm just going to have two intervals now, I0, I1. And so my sum is just as before, but I'm just doubling up. So sum is identify blue intervals in pairs. Okay, I know which one is the first, which one is the second, and I take the first and the first and the second and the second with the same gluing as before. And then I'm going to take X to be simplest element here, which is a disk with two intervals in its boundary oriented in the same way, like this. Okay, so this is my I0, I1. So that's at least an object in the category. If I take X plus X, then if I try to glue a disk with two intervals in its boundary, and I want to a copy of X, and I want to identify the intervals, well, I'll get a picture like this, right? So what I get is a cylinder. So I told you what M plus and X was. We're missing this B, this little element in the mapping class group. So I'm going to take, so first, what is the mapping class group here? Pi naught diff of, this is OUT, this is our OUT X plus X, right? This is by definition pi naught diff of isomorphic pi naught diff S1 cross I. So again, it's relative to the boundary. The mapping class group of the cylinder, and the mapping class group of the cylinder, let me draw it like this. The cylinder is generated, the mapping class group is generated by a single Dane twist here. You can take this circle and do a Dane twist, so turn it around itself. So this is isomorphic to Z, and this is generated by the Dane twist. On this middle circle. Okay, and I'm going to take B in here to be a generator. Oh, it's inverse if I have to be honest, but you won't see the difference. Okay, so that's at least an element in here. And now you can see that it starts looking, especially when I draw the cylinder like this, it starts looking a little bit like these surfaces before. So what is going on is, the fully honest picture is this. I have the cylinder, and we have our little circle here, right? Where we do that we use for the Dane twist. When I keep track, if I keep track of the intervals when I glue, and if I pay attention to what I'm doing, what I'll find out is my new intervals. One of them is going to be above, and the other one is going to be below. It means that when I glue the next disk, we have to talk about the braid relation in you know, 3 copies of X, the next disk is going to be here. And I'll get a surface of genus 1 with, one boundary component. And the next circle, you know, it's going to be here, right? Somehow, something like this. It goes off the surface, right? But like this. Like that. Anyway. You want the board lower? I know, I just wanted to show the picture first. So I can relower because I was seeing people, but maybe you were just trying to tell me to lower it. I don't know. Anyway.
You might be able to see one.
Yeah, the question is, you know, it's the audio, you know, I think this picture for the audience here is more important than the line above. That was what I had run. Anyway, sorry, Toronto, if I'm not treating you well. So, any other complaints? Okay, I'll do some erasing. Okay, so we have 2 examples, right, of these Yang Baxter elements. They're quite different, or they have a quite specific difference. Is the first one is actually part of a braided. It's a braiding for a braided monoidal structure. The monoidal category is braided, and this is the braiding. Whereas the second one, this element, it does come from a map from the braid group, but it's not natural. The naturality condition fails a little bit. There's the hyperelliptic involution of the surface sort of comes in the way. Okay, so I have to get back to homological stability now. And so that's the plan. Yeah, I'll start with a construction. So given the data we have, so we have this monoidal category. We have this element X. We have maybe another element A. Want to shift things a little bit, and we have this B in aught X plus X, which is a Yang Baxter element. Then from this data, you can construct a semi-simplicial set. For every n, that comes with an action of the group of automorphisms of A plus X plus n. And it's just defined like this. You take the automorphism group of this object we are looking at, mod it out by, so the P, I have to tell you what the P simplices are, and the P simplices I'm just going to mod out by a subgroup. So just as a set. So this is aught A plus X plus N minus P minus 1. So I mod out by a part of the automorphisms of a part of this object, and the face map di, maybe I start with d0. If I want to go to the p-1 version, when I go to the p-1 simplices, I'm dividing out by a slightly bigger group. So there's a natural projection map. So this is just a projection map. And then if I want to do a di, I'm going to use my b to twist, and I'm going to twist this by a block braid that looks like this. So if I have a way to pass, I have a way to pass, I'm looking at whatever. I have a way to pass x and x with x, and I'm going to take the ice copy of x and move it by a twist. It looks something like this. I pass I copies of x with an x. So this is a composition of this element b. And here's a little fact, is that the Yang Baxter equation for b implies that this is simplicial. It implies the simplicial relation. So I dare to do this. I was going to draw the picture, but I think the picture is going to take too long. There's a very nice picture you can draw. So, okay. So maybe the slightly funny fact is that, this Yang Baxter equation was this thing with 3 terms equal 3 terms. And the simplicial relation is 2 things equals 2 things, right? It's di equals di plus 1, this way around. Anyway, it's 2 things. But once you write down the simplicial relation, you find out that the difference between the 2 sides, there's sort of, when you do the di plus 1, there's an extra twist. And the Yang Baxter relation allows you to move the extra twist into this group we're quotienting out by. That's the rough idea. So anyway, not too far. Okay, so this object, this space, you can naturally you can construct given this data is useful and related to stability for the following reason. So the theorem. So this is essentially in work of Randall Williams and myself, but this was improved by Manuel Kranich, and I'm giving a version here that includes his improvement, and it says the following. So in this particular situation, if there exists a k at least 2, such that these spaces W and AX is n minus 1 over k connected for every n. If I know some connectivity of these spaces, then stability holds for these automorphism group Hi out a plus x n times to Hi out a plus x plus n plus 1 times. This is necessarily an isomorphism for I smaller equal to n over k. Plus, some twisted coefficients versions. So a bunch of things hold true. Okay, so there are a lot of groups that fit in this framework. You can take your monoidal category to be R modules with the direct sum and get general linear groups under some conditions to have the connectivity, but still you could take vector spaces equipped with a form and get things like symplectic groups, unitary groups, or you could take free groups or groups and the free product. In some cases, you can take groups and the direct product, and so on. I mean, there are a lot of examples. There's an issue though. Issue for us is that 3/2 is smaller than 2, right? So I have this little assumption here, and this comes from the shape of the argument. It uses a spectral sequence, and the spectral sequence doesn't want to do anything that has anything to do with k smaller than 2. So, okay. So 3/2 is, and this is, you know, where does this come from? Well, we are thinking of our surface as G1, say, as, you know, this is the surface, it's a genus 1, and so on. And we counted the genus and we said, oh, there are G of them. And this is sort of our rank in this theorem, right? But this is now, I wish I had this extra board. Okay. But what did we do in this, in our little investigation of Yang Baxter elements? We found this other Yang Baxter element that came from considering the surface as a bunch of disks glued together. So here's the thing. So three is at least 2, right? 3 is bigger than 2. And so if we look at the surface, the same surface as, sorry, SG1, it's also in our new sum, it's made out of 2G disks. So we have changed the rank in this, and so we can apply the theorem. And so the thing we prove with the other Oscar and Max is that the space in this situation for the M is this bimarked surfaces. Then in this case, Wn, or some surface with the disk, where S is, to be precise, it's some surface, but it has its interval in the same boundary components. Then this is N minus 4/3 connected. Plug it in the theorem, be a little bit careful about your statement, and you output the statement I had at the beginning of the hour. That's that.